Hi there and welcome. We are going to be talking about limits and the derivative today. This is section 1.4. The definition of limit. Let g of x be a function and a be some number. We say that the number L is the limit of g of x as x approaches a, provided that g of x can be made arbitrarily close to L for all x sufficiently close but not equal to a. In this case, we write the limit as x goes to a of g of x equals L. Oh my goodness, that's a lot. Let's see what that means. So we're going to look at this graph and decide whether the limit exists for some function f of x equal to 1 over x minus 2. Now if that limit exists, we're going to find the value. So let's look at this function. I've graphed it for you, the 1 over x minus 2, and I see that I have a curve. It's in two separate pieces. From the left it goes down, and on the right it also goes down. So I want you to look at this. If I'm looking at this graph and I am looking at it as I walk along the graph from left to right, as I go from the left, I'm decreasing. Now at 2, I have a vertical asymptote because if x were 2, I would have 0 in the denominator. So that would mean that something funny is going on. Now in this separate piece, as I look at it from left to right, I'm also going down. So as x approaches 2 from the left, it appears that f of x is going to negative infinity. As x approaches 2 from the right, it appears that f of x is approaching positive infinity. We would say that since the limit from the left does not equal the limit from the right, the limit of f of x fails to exist, and we would write it as the limit as x goes to 2 of f of x equals dne, meaning does not exist. So let's look at another one, maybe one that does exist. So let's look at this limit and see if it does exist. So we're going to make a table of values and see what happens with the table of values. So I see that as x is getting closer and closer to 4, first off we look at 4.1, then 4.01, then 4.001, 4.001, 0001 I think. As we get closer and closer to 4, that's what we're looking to do, get closer and closer to 4. Our numbers are getting closer and closer to, looks like to me, the number 57, but I'm not for sure. Looks like it starts off around 62, then goes to 57.5, then 57.05, then 57.005. So it appears to me that it's going to 57. Let's look at it from the left, so from the other direction. We're going to 4, starting at 3.9, then going to 3.99, 3.999, then 3.999, getting closer and closer to 4. And let's look at the value of our function as that happens. So I have 52.3, 56.5, 56.95, 56.995. Once again, it appears as though my value is going to 57. And if you were to plug in the 4, and there's nothing wrong with me doing that, I can do that, 4 cubed minus 7, I would see that I would get 64 minus 7, and that would indeed be 57. Let's see what we have next. So if I'm to look at the absolute value function, this absolute value function, let's see if as x goes to 3, if the limit exists. We need to decide whether or not the limit of as x goes to 3 of g of x exists. And if it does, we're going to give the limit. Now this happens to be the function g of x equals the absolute value of x minus 3, and then added 2. So if you want to graph that, you can. That's what we've got here. However, we have a hole at x equal 3. That's the difference in this particular graph. We have a hole there. And we can see that as x gets closer and closer, my values of g are approaching 2. It doesn't matter that g of 3 does not exist. As long as it's true from the left and the right, and as we get closer and closer to 3, then our limit exists. Here are the limit theorems. If the limit as x goes to a of f of x and the limit as x goes to a of g of x both exist, we can use these following results. Number 1, if k is a constant, then the limit as x goes to a of this constant times f of x equals just the constant times the resulting limit. And that's called the constant multiple rule. If r is a positive constant and my quantity f of x is all raised to the r as defined for x not equal to a, then the limit as x goes to a of the quantity f of x all raised to the r is just find the limit and raise that to the r power. That's the powers of a limit. Rule number 3, the limit as x goes to a of the quantity f of x plus g of x equals the limit as x goes to a of f of x plus the limit as x goes to a of g of x. This is called the limit of a sum. Number 4, the limit as x goes to a of f of x minus g of x is the same thing as the limit as x goes to a of f of x minus the limit as x goes to a of g of x. This is the limit of a difference. Step 5, or Theorem 5, is the limit of a product, and this is the limit as x goes to a of f of x times g of x is the same as the limit of each of those two functions multiplied together. The limit of a quotient, as long as your denominator doesn't go to 0, then the limit of as x goes to a of f of x over g of x is just equal to those resulting limits divided by each other. We have 2 more limit theorems. Limit theorem number 7, the limit of a polynomial function. Now, if p is a polynomial function and a is any number, then the limit as x goes to a of that polynomial is just p of a, meaning just plug that a in. That makes it nice. The limit of a rational function, theorem number 8, let our rational function r of x equal p of x over q of x be some rational function where p and q are both polynomials. Let a be a number such that q of a is not equal to 0. Then the limit of this rational function of x as x goes to a is equal to r of a, meaning just plug in the value of a. So let's do this. Let's compute the limit if it exists. I look at this, and since evaluating the denominator of this function at x equal 1, 1 plus 1 is 2, it's not equal to 0, we can use limit theorem 8 for the limit of rational functions, meaning we can just plug the value of 1 in. And that's what we will do. And we will get a value of 1. All right, next, let's compute the following limit if it exists. This is the next example. So I have the limit as x goes to 3 of negative 10x squared plus 30x all over x minus 3. So for our solution, we will notice that since evaluating the denominator of the given function at x equals 3 is 3 minus 3, we cannot use the limit theorem 8 for the limit of rational functions. We can't just plug in our value of a, which is 3. So what we're going to have to do is we're going to have to manipulate this guy a little bit. So what I'm going to do is I'm going to look at that numerator and I'm going to say, hey, both of you two guys have a negative 10x in you. So I'm going to factor that out. I'll notice that I can then cancel those two terms, leaving me with the limit as x goes to 3 of negative 10x, giving me negative 30. Let's try another one. Compute the following limit if it exists. The limit as x goes to 6. Now, I can't really think of any way that I can work with this one to do any canceling. If you can cancel, fine, that works great. I can't plug in the 6 since evaluating the denominator of the given function at x equals 6 gives me 6 minus 6, which is 0. We cannot use the limit theorem 8 for the limit of rational functions. So what I usually like to do when I'm looking at this and I think, well, I don't know what else to do, I'll graph it. So I've graphed this function, and I will notice that at x equals 6, which is right here, I do not have a limit that exists, and it verifies what I already knew, and that was that the limit did not exist. So for a definition of differentiable, a function f is differentiable at x if f of x plus h minus f of x all over h approaches some number h approaches 0. It's kind of a weird statement there, isn't it? The function f of x, the absolute value of x, is an example, is differentiable for all values of x except for at x equals 0 because of that corner there. Since the graph of the function has no definite slope when x equals 0, f is non-differentiable at x equals 0, but it does have a definite slope since the derivative or differentiation has to do with slope and it gives the value of the slope. It does have a slope for every value to the left of 0 and every value to the right. Here's the limit definition of the derivative. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. When we're going to use limits to calculate f prime of a, we number one write the difference quotient, f of x plus h minus f of a all over h. We simplify that difference quotient, and then step 3 we'll find the limit as h goes to 0. This limit is f prime of a. So in order to use the limit definition to find the derivative of a given function, and I just gave you f of x equals 2x plus 3, what we're going to do is first write the difference quotient, and then we'll plug in our x plus h wherever there was an x. So I have the limit as h goes to 0 of 2 onto x plus h plus 3 minus the quantity 2x plus 3 all over h. Now simplifying that, I'll distribute the 2. The limit as h goes to 0 of 2x plus 2h plus 3 minus 2x minus 3. I have a few things that will cancel there, leaving me with the limit as h goes to 0 of 2h over h. I have another canceling situation that'll happen, and I just have the limit as h goes to 0 of 2. I'll use the limit theorem for a constant and say that that limit is 2. Next up, we're going to talk about limits as x increase without bound. In other words, we're talking about the end behavior and isotopes of rational functions. So let's suppose that we have some f of x where p of x and q of x are rational functions where p of x is some polynomial and q of x is another polynomial. P of x has a degree of m, q of x has a degree of n. So if the degree in the numerator, m, is greater than the degree in the denominator, n, then the limit as x goes to either positive or negative infinity of f of x equals 0, and y equals 0 is a horizontal isotope. We're going to say that limit is 0. That's what we are looking for. I call these functions when the degree in the numerator is less than the degree in the denominator. I call those bottom-heavy functions because the degree in the bottom is heavier than the degree in the numerator. The bottom-heavy functions, the limits go to 0. I call this an evenly balanced function if the degree in the numerator, m, equals the degree in the denominator, n. So we have that the limit is the ratio of the coefficients as x goes to either positive or negative infinity. I call these evenly balanced functions. And evenly balanced functions will just be the ratio of the coefficients. And if the degree in the numerator is greater than the degree in the denominator, my limit is either going to go to positive or negative infinity. I'll call those top-heavy functions. And now let's look at an example of each of those. So I look at this function, I notice that the degree in the denominator is bigger than the degree in the numerator. This happens to be my rule A. So this is a bottom-heavy function. That means my limit is going to be equal to 0. Let's verify that by looking at the graph. Notice as x goes to infinity, my y's are going to 0. So either positive or negative infinity, this is going to 0. I can conclude by saying this limit is then 0. Let's look at another one. This one happens to be what I call an evenly balanced function. On evenly balanced functions, I take the ratio of the coefficients. So let's look at this on a graph. Notice that as x goes to infinity, y is going to 3 on both ends. So I can formalize this by saying that the limit of this guy as x goes to infinity is 3. Lastly, I'm going to look at a top-heavy function. Top-heavy functions have the rule that if the numerator is greater than the denominator, then my limit's either going to positive or negative infinity. So let's look at this. As x goes to positive infinity, y's are going to negative infinity. I would write that just like this. As x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, this way, y is going up to positive infinity, and that is how I would write that last one. All right, that concludes section 4 video. Let me know if you have any questions. Bye now.